one of the special guest lectures by Keith Conrad. This time we will be talking about Wieferich primes.
Okay, thank you. So before I explain what a Wieferich prime is, I want to show you some numerical patterns that will lead us into appreciating what the concept is all about. So the first thing, just to start with something totally elementary, you could imagine a student in grade school just might be looking at patterns of decimal expansions, and maybe they want to see what are the patterns in the decimal period of some unit fractions. So 1 over n, if n is relatively prime to 10, is a purely periodic decimal, and we'll write d of n for the period. So 1/7, 0.142857 repeating. D has length 6, so d of 7 is 6. 1 over 37 has a period 3, so d of 37 is 3. And you can show the decimal period of 1 over mn is the least common multiple of the decimal periods of 1 over m and 1 over n if m and n are relatively prime. So if you wanted to calculate the decimal period of a unit fraction, it really boils down to understanding the decimal periods of prime powers, where the denominator is a prime power. So if we look at a table of some examples, then we see here that if you read across the table, I'm listing the decimal period for 1 over powers of 3. So 1/3 is 0.3 repeating, 1/9 is 0.1 repeating. Is that right? Yes? No? Yes. But after that, if you go to 1 over 27 or 1 over 81, then you start to have decimal periods of length bigger than 1. On the other hand, for the higher primes, 7, 11, 13, and 17, you see once you figure out the decimal period for 1 over p, for 1 over the powers of p, higher powers, the decimal period of those unit fractions is actually the decimal period for 1 over p just multiplied by the prime. So if you read across the row, for example, for 1 over 7, 1 over 49, and so forth, the decimal period just goes up by a factor of 7 every time. So you can naturally ask, is this always going to continue? For example, the reciprocal powers of 3 is the decimal period for 1 over 3 to the k. Is it going to be 3 to the k minus 2 once k is at least 2 in the first row? And so that turns out to be yes, but if we asked the same question about the higher the powers of primes bigger than 3, if the period length is always p times the previous one, or just simply is the decimal period p to the k minus 1 times the decimal period for 1 over p. And that seems to be the case for 7, 11, 13, and 17. And it really is the case that the decimal periods for higher powers, you just keep multiplying by an additional power of p. The only variation is really what's the length at the very beginning. Then you just start multiplying by powers of p. And so it is true for 7, 11, 13, and 17, this pattern that we see across the rows of just multiplying by the next factor of p is true. However, this pattern is not always true. There are some primes where this apparent pattern breaks down, and the first time you'll see that is at the prime 487, and at this prime a little bit above 56 million. For these cases, 1 over p and 1 over p squared actually have exactly the same decimal period. It doesn't go up, but after that point, then you just start multiplying by powers of p. So it's just like what we saw when p was 3. So you have to wait a little bit, and then the pattern kicks in. So the source of this phenomenon is that in terms of algebra, that the decimal period of a unit fraction is, if the denominator is relatively prime to 10, is really just the order of 10 in the units mod n. Just look for the subgroup of powers of 10 and see how many different powers of 10 you have. For example, 1 over 7 has a decimal period of 6, and 10 mod 7 has order 6. And so those two values are related to each other. They're always equal. So that's the group theoretic interpretation of the grade school idea of looking at decimal periods. Actually, Gauss, some people proposed that maybe Gauss developed modular arithmetic because he was trying to understand the periods of decimal expansions. I mean, before Gauss, I mean, what was there in number theory? You know, you're futzing around with some, well, I guess Fermat proposed Fermat's last theorem, but you know, back then in the like around 1800, you know, understanding patterns in decimals, there's no calculators. People wanted to be able to predict these things without having to work them all out by hand of their properties. And so Gauss was led in part to develop modular arithmetic by questions about decimal expansions. So once we have this group theoretic interpretation, then we can understand some properties. For example, well, a subgroup will always have size dividing the size of the group. So d of p, the period length for 1 over p, will always divide p minus 1. Like when p is 7, d of 7 does divide 6. In fact, it's equal to 6. D of 37, we saw was 3, and that is a factor of 36. So we've seen that. And in general, d of n will divide phi of n, the number of units mod n, or d of p to the k will divide this number here. This is phi of p to the k, the number of units mod p to the k. And the least common multiple property also comes from this group theoretic interpretation of decimal periods. If you use the Chinese remainder theorem, it explains why you have this LCM property. Okay, so we looked a bit about decimal periods. They seem to have some patterns, although the parent pattern we saw before with the primes above 3 eventually breaks sporadically at those two examples. So let's talk about binary expansions, base 2. So you can do the same thing if you look at the expansion of a unit fraction with an odd denominator. 1/7 has a binary period of 3, or 1/5 has a binary period of 4. And again, the binary period behaves well on relatively prime numbers. Its value on a product is the least common multiple. And so it's enough to understand the binary period for powers of odd primes. And if you look at this table and read across the rows, you see once you know what the period is for 1 over p, the higher powers of p have their binary expansions admitting a period that you just multiply by the next power of that prime. And it's the same pattern across every row. The only funny thing is what's happening at the beginning, but once you know the binary period of 1 over p, everything else seems predictable. But this apparent pattern here is not, in fact, always true. The first time that this rule of successively multiplying by p to get the binary period of the next reciprocal prime power, first time it breaks is for the primes 1093 and 3511. So we will see these numbers later on. So if you see them, you should think back to this phenomenon. For these two primes, 1 over p and 1 over p squared have exactly the same binary period, but once you get past that, then you still have the pattern like we saw for 3 and for 487 and for that 56 million number for base 10. In these cases, the binary period goes up by powers of p, but you have to wait until you're past the first reciprocal power. And just like before, in fact, the binary period is nothing other than the order of 2 mod n, and so it explains various patterns, just like we saw when we were looking at decimal expansions. And so that's what I want to say about these two things. So if you look at expansions in some base, then sporadically, sometimes 1 over p and 1 over p squared will have the same period in that base. But if you go far enough, then the pattern is you just multiply by powers of p. But you might have some problems at the beginning sporadically, like in base 2 for 1093 and 3511. Are there any questions? Yes. We'll get to that. We'll that's coming up. It was a research topic in the in the early 1800s. That's true. But all right. So the third numerical pattern I wanted to present to you before we get to defining Wieferich primes is a totally different topic, and it's the question of calculating the ring of integers of a number field. So, for example, the ring of integers of q adjoining the square root of 2 is z bracket the square root of 2. This is one of the things that Hansen brought up in his lecture earlier today. And what about higher order roots? If I take q adjoin the nth root of 2, is the ring of integers z bracket the nth root of 2? And the answer is yes for all n up to 1,000. So therefore, surely it's true for all n, but kind of the whole thrust of the way the presentation has been going, presumably the answer is going to be no. There will be counterexamples, and this pattern, in fact, does break, and the first time it breaks is at 1093. In other words, the ring of integers of q adjoin the 1093rd root of 2 is bigger. It's not z bracket the 1093rd root of 2. It's actually something bigger. And in fact, if you replace the roots of 2 with roots of 10, if you look at the ring of integers of q adjoin the nth root of 10, then for all n up to 1,000, the full ring of integers is z bracket the nth root of 10, unless n is divisible by 3 or 487, which are the numbers that we saw before had the funny behavior for the decimal periods. There was also the number around 56 million, but that's above 1,000, so we're not going to encounter that just yet. So as an example, if you took n equals 3, in q adjoin the cube root of 10, this is inside q adjoin the cube root of 10, what we see is that you can have an algebraic integer that, in terms of sums of powers of the cube root of 10, does not have integral coefficients. Here the coefficients are all 1/3. Okay, in fact, there's an example of a monic polynomial with integer coefficients that has that number as a root. So the ring of integers is bigger than z bracket the cube root of 10. And yeah, so we see these numbers again, 3 and 487. And in fact, if you went out to 56 million, I didn't write it down here, 598,313, you'd run into another problem with this question of determining the ring of integers of q adjoining the nth root of 10. Okay, so we've seen these kinds of funny numbers, 3 and 487 or 1093, showing up in two rather different contexts. So we'd like to kind of understand, why is there a connection between the appearance of these funny numbers in these two very different settings? What do decimal expansions or binary expansions have to do with computing a ring of integers inside of a number field? Any questions? All right, so the connection comes from relating them both not directly to each other, but to a certain kind of extension or refinement of Fermat's little theorem. So Fermat's little theorem tells us that when a is not divisible by a prime p, that a to the p minus 1 is 1 mod p. Well, what if I wanted to impose a higher order congruence on that? Could they be congruent modulo p squared or p cubed? So it turns out, if you contemplate the congruence that's boxed there, for each modulus p squared, p cubed, there are always p minus 1 solutions. So in the table here, I presented writing this. When I say p minus 1 solution, I mean modulo p to the k. Of course, once you have a solution as an integer, you can add p to the k and get more solutions. But if I want to count solutions mod p to the k, there are always exactly p minus 1 solutions for every power of p as the modulus. So in the table, if we look at a to the 4, p is 5 here, then we have, of course, the familiar Fermat little theorem. All non-zero numbers mod 5 have a fourth power of 1. But if you look at the modulus 25 or 125 in the second and third columns, then you still only get 4 solutions, and they're actually related to the earlier solutions. They start, if you wrote them out, if you write out the 4 solutions in base 5, they start with a 1, 2, 3, and 4 plus a multiple of 5. And then if you look at the solutions to the congruence mod 5 cubed, there are 4 solutions. And if you look at the base 5 expansions of the solutions, you can detect the earlier solutions. If you can solve the congruence mod a power of p, you can reduce the solution to the lower powers and still get solutions to the earlier congruences. So that kind of is why you have this consistency. So I don't know if Christelle, did she say something? We're starting to see like power expansions and powers of 5. And so there is something kind of p-adic here if you took higher and higher powers of p, but it's not exactly the direction that I want to go in. But I just want to point out there is something p-adic you could say about this kind of situation, trying to look at the equation. If you looked at the equation x to the p minus 1 equals 1, did she talk about the p-adic integers? Yeah, in the p-adic integers, it has p minus 1 solutions, and they kind of can be built up in this way by solving this as a congruence modulo higher and higher powers of p. So while we can always solve the congruence no matter what power of p you put there, and the number of solutions is always the same, if you change things around, instead of starting with the prime and looking for the a's that fit, if you start with the a and look for the p's for which this can be done when the modulus is bigger than p to the first, things get much more complicated. So let's fix the a first, and then let's look for primes where a to the p minus 1 is 1 modulo p squared, not p, but p squared. This is a much more delicate thing, starting with the a and looking for the p's that kind of get a stronger version of Fermat's little theorem. And so when you can do this, we say that the prime p, call it a Wieferich prime. Wieferich is the name of somebody. We'll see later on who that is and what his connection is with this congruence. So we call such a prime a Wieferich prime to base a. So for example, you can take for the a equal to 10, you could use the prime 3. 10 to the 3 minus 1. 10 squared is 1 mod 3 squared. In fact, 10 is already 1 mod 3 squared, but it's still true that 10 to the second is also 1 mod 3 squared. So 3 is a Wieferich prime to base 10. And it's this congruence, kind of making Fermat's little theorem be true mod p squared. This is going to be the thing that links the previous patterns that we saw. So let me show you a table of some examples of these Wieferich primes. There's the definition again. Wieferich prime p to a base a just means that you can get this congruence to work modulo p squared. So it turns out the only known Wieferich primes to base 2 are our friends 1093 and 3511. So here we're trying to solve 2 to the p minus 1 is 1 mod p squared. And those are the only known primes that fit to this day. They were found long ago, but it's been checked up to like 10 to the whatever, 15, 10 to the 18. No further examples have been found. If you took a to be 3, we only know 2 Wieferich primes to base 3. It means 3 to the p minus 1 is 1 mod p squared, only for the 2 primes you see in the row for p equals 3. For the prime 5, we actually know a whole bunch of p's that make that congruence work when a is 5. I don't think there's any conceptual reason why it's so many more solutions. The ones I've listed there and 2 further ones are the ones that have been found. For base 10, a is 10. There are 3 examples. We've seen these numbers before, 3, 487, and the 56 million number. No examples are known for 47. If I wanted to find a prime that makes this congruence work that I'm writing down here, nobody's ever found such a prime. Okay? So again, to emphasize the point of view here, if you start with the prime p, you can always find a's that make a to the p minus 1 be 1 mod p squared, because there's always going to be p minus 1 solutions, mod p squared, and then if you increased a by adding p squared to it, if you had an a prime that was congruent to a mod p squared, it would also work. So there are infinitely many a's for each p. But if you started with the a and then looked for the p's that make the congruence work, kind of like Bayes' theorem, you kind of switch out the roles of what you're looking at, and things get much more subtle. If you pick a first and hunt for p's that make the congruence at the top work, it's very hard to find these examples in practice. Okay? So these are Wieferich primes, and this congruence here is behind the phenomena that I mentioned at the beginning about the 1 over p and 1 over p squared unexpectedly having the same period length in base 10 or base 2, or the funny ring of integer calculations. There's a question in the back. Yes. Yeah. No. I think it's fine. Oh. Yeah. So I was just checking that you were paying attention. And you're done. Okay. Yeah. All right. Thank you. Other questions or comments? Yes? Well, like 47, we've never found an example. Oh, is it known that there is one? So I will come back to this question, which is a good question. Is there at least one? Are there infinitely many or finitely many? What can we say? So we'll address that later on. I saw a hand in the back. Yes? That will come up later too. I've planned all this out. Yes? Well, so there's a good question. What yeah, how would you even go about trying to guess this? They seem very rare. Should they stop? So I will present what the current consensus is, what the conventional wisdom is on how this should turn out, whether it's true or not. But we'll have a definite common belief by the end. Right? So there's again the definition at the top, the Wieferich primes. So what's the connection to the base expansions? Well, it's that if you ever have a number a that's not divisible by a prime p, then if you can look at a mod p, you can look at a mod p squared, and if you calculate the order, the lowest power of a that will bring you back to 1, the order of a mod p squared has two options in relation to the order of a mod p. Typically, meaning if a to the p minus 1 is not 1 mod p squared, the order of a mod p squared is just p times the order of a mod p, that kind of multiplied by p pattern that we've seen before. But if a to the p minus 1 is 1 mod p squared, then they're exactly the same order. Okay? So when a is 10, this is the pattern I presented to you before, that like for the primes 487 and 3, the d of p squared could sometimes be d of p. It's typically d of p times p multiplied by p. But if 10 to the p minus 1 is 1 mod p squared, then the decimal period does not change, because the decimal period is the order of 10 mod p and mod p squared. And the same with a equals 2. It connects up with, you see, I've written a, not p. See, I had it correct here. That the binary period is either going to, for p squared or p for 1 over p squared and 1 over p, will either be usually p times bigger, or sporadically it'll be exactly the same. Okay, and that's only known for the primes 1093 and 3511. So that's the only known cases are these two. Okay, there could be more, but none have ever been found. So typically, the usual thing is that the power a to the p minus 1 is not 1 mod p squared. Very unexpected for that to happen. And when it does, you have this kind of funny behavior. The connection with the ring of integers is that if you have a square-free integer, then the ring of integers of q adjoining the nth root of a is z bracket the nth root of a exactly when the prime factors of n that don't divide a have a to the p minus 1 not 1 mod p squared. And when it is, you get some weird stuff. So for example, take n equal 2. Its only prime factor is 2. And so we have to be careful if 2 to the p minus 1 is 1 mod p squared. You see, if you took n equal to 2, it's saying that q adjoining the square root of a has ring of integers z bracket the square root of a, except if when a is if a is not divisible by 2, you don't want, it would be bad if a were 1 mod 4, right? If you take p equal to 2, the congruence I highlighted there, saying a is not 1 mod 4 is good. Okay, so a could be even or a could be odd, but if it's odd, 2 doesn't divide a. It would be very bad if 2 to the p minus 1 were 1 mod p squared. So if a were 1 mod 4. And so that connects up with the condition that Hansen mentioned. The ring of integers of a quadratic field is z bracket the square root of that number exactly when a is not 1 mod 4. Right? So 2 is a, I guess if, well, the prime 2 is a Wieferich prime for any odd number a that's 1 mod 4. Yeah. Or if you took a to be 2, instead of fixing n, if you fix a, we get back the property I mentioned before. Q adjoining the nth root of 2 has ring of integers z bracket the nth root of 2, as long as the odd prime factors of n don't have 2 to the p minus 1 being 1 mod p squared. You run into problems. The first problem is at 1093. And that's when it's bigger than what you might expect. Just like q adjoining root a, the ring of integers is bigger than what you might expect if a is 1 mod 4. Q adjoining the nth root of 2 has bigger ring of integers than z bracket the nth root of 2 if there's a prime factor of n, an odd prime factor for which 2 to the p minus 1 is 1 mod p squared. And then you get more stuff. Any questions? Okay, so let me briefly mention there is a connection. Question, yes? I'm sorry, you're asking if you can refine that. Do you just mean increasing the modulus? Yes. So I'll just, I think somebody asked about that before. So I'll bring up the, right, you made, what about mod p cubed and so forth? Yes, so we'll this has been planned out. Okay. So so there is a connection, I'll just mention briefly, between the Wieferich primes to base 2 and the question of whether Mersenne numbers 2 to the q minus 1 are or are not square free. So a Mersenne prime is a prime of the form 2 to the n minus 1, and the exponent has to be a prime number if there's any chance that 2 to the n minus 1 is going to be prime. But typically, even if the exponent is a prime number, 2 to the q minus 1, it's typically not prime. Does anybody know how many Mersenne primes are known? Yes? 51. Okay, something like 51, 52. I think. Okay, well, all right. I mean, but there probably hasn't been any changes since then. There were only, well, the numbers were always there. Okay, so even when they're not prime, still people observe that when they're able to factor them, these get so big it's very difficult to factor them. But when they can be factored, they always appear to be square free. And so the question came up: could 2 to the q minus 1 fail to be square free? Must it be square free if q is a prime? By the way, if you use the exponent 6, 2 to the 6, what's 2 to the 6 minus 1? 63, not square free. So the constraint of making the exponent a prime, this is a good thing. So it turned out, as I mentioned at the bottom of the slide, if there's ever a repeated prime factor in a 2 to the q minus 1, that number, that prime has to be a Wieferich prime to base 2. And in fact, the only two examples that are known, 1093 and 3511, are known to never occur as a repeated prime factor of a Mersenne 2 to the q minus 1. We've never found, and it's believed, that 2 to the q minus 1 is square free when q is prime. And so unless we find some more Wieferich primes to base 2, it's unlikely we'd actually find an example of a non-square free 2 to the q minus 1. Okay. So where does the name Wieferich comes from? Arthur Wieferich, the German mathematician. I think after he finished grad school, he then went off and did something else. But in his early 20s, he was working on some problems connected to Fermat's last theorem. So if you want to solve Fermat's last theorem, show that the equation, the boxed equation there, has no positive integral solutions. Well, you can simplify the task down to checking no solution when n is 4, or no solution when n is an odd prime. I don't know if Hansen mentioned, did you discuss this at all? Okay, not yet. Okay, so so you don't have to try to show the general equation can't be solved, but just focus on these exponents. Fermat himself treated the case n equals 4, and the entire problem, so we only have to worry about showing there's no solution for an odd prime exponent. Euler did p equals 5, and so forth. There's kind of gradual progress, and then about 30 years ago, Wiles, with the help of Taylor, solved the whole thing. Now, before Fermat's last theorem was settled by Wiles and Taylor, the progress was always incremental. It was never proved before the whole problem was solved. It was never proved that Fermat's last theorem was true for infinitely many prime exponents. It was always just checking prime by prime by prime, developing new criteria. And for example, it was only actually proved for the primes below 4 million until the whole problem was solved by totally different methods, using nothing about all the step-by-step approaches that have been taken before Wiles made his announcement. So the traditional approach to Fermat's last theorem, going back to Sophie Germain and Kummer, was to consider two cases for exponent p. Show case 1, there's no solution x, y, z where p doesn't go into any of them. And then case 2, show there's no solution x, y, z where p is a factor of one of them. And traditionally, the criteria that were developed to verify that, yeah, case 1, no solution, or case 2, no solution, the case 1 criteria were always much easier to apply, just how things happen. Of course, once Wiles solved Fermat's last theorem, this whole case 1, case 2 thing just disappeared and nobody cared about it anymore. His approach had nothing to do with this case division at all. But this was the traditional way that things were worked with for Fermat's last theorem before the 1990s. And in particular, Wieferich had shown that if case 1 fails, if there were a counterexample, if there were a solution to Fermat's last theorem for exponent p, and p didn't divide x, y, or z, then 2 to the p minus 1 would have to be 1 mod p squared. Very surprising, not at all obvious where this comes from. It's the end result of a chain of calculations. And in fact, at the time of Wieferich's announcement of this result, there weren't even any such primes known. The 1093 and 3511 were only found afterwards, okay, in 1913. Oh, 1922, 100 years ago. Okay, so, and that was it. No more examples were ever found. So after that, there was some further progress in other similar criteria, showing if case 1 fails, then 3 to the p minus 1 is 1 mod p squared. Now, no prime 1093 and 3511 that fit the congruence for 2, they don't fit the congruence for 3. Okay, so that kind of takes care of case 1 for all those two primes, and anything since then, nobody's found any more solutions for that congruence. And then people started to, once it was discovered the base 3 also would be a consequence of case 1 having a counterexample. People did for 5 and 7 and 11. And in fact, just before the whole problem of Fermat's last theorem was settled, people had been able to show this kind of criterion is a consequence of case 1 not working with all prime bases up to somewhere around the order of 100. Okay. Of course, nobody cares about this anymore after Fermat's last theorem was settled, but I did point out, like calculating rings of integers of these kind of radical field extensions, the condition of a to the p minus 1 being 1 mod p squared or not, it does affect what the ring actually looks like. Okay. And again, just to emphasize, solving case 1 of Fermat's last theorem does not solve Fermat's last theorem for the exponent, right? If you want to show that you've settled Fermat's last theorem for a particular exponent, you have to deal with case 1 and case 2. So even though in 85, Adelman and Heath-Brown proved case 1 has no solutions for infinitely many primes, they did not settle Fermat's last theorem for infinitely many primes because they didn't say anything about case 2. Now let's address the question. Actually, before we get to this question, I have a question. How long do I have to speak? Because I don't remember when I started. Does anybody remember when I started? Okay, thank you. So let's address this question of how many Wieferich primes should we expect? Finitely many? Infinitely many? So the approach to addressing this question heuristically is to take Fermat's little theorem, a to the p minus 1 is 1 mod p, and expand it mod p squared. It's 1, a to the p minus 1 is 1 plus a multiple of p, mod p squared. So 1 plus bp. B is some number from, say, 0 to p minus 1. Or we can even solve for b. B is a to the p minus 1 all over p. Now modulo p, we can determine b from a. So the basic idea is to pretend, to assume that that number b is some random number mod p. We get a Wieferich prime when b is 0, but typically it's not 0. And not knowing anything about the behavior of these numbers, we'll just assume that the b behaves like a random number mod p, so it could take any of the values mod p with equal probability, whatever that means, say 1 over p. For each chance, could b be 0 or 1 or 2 up to p minus 1. Every instance could have probability 1 over p. So what that suggests is if you wanted to count the number of Wieferich primes to base a for the primes up to x, you'd sum over p up to x the probability that p is a Wieferich prime to base a. This is very, very serious, like heavy, like quotes, probability, whatever that means. But if you think about it as maybe it's random mod p, these probabilities, maybe they're all 1 over p, independently of the base. And so how does the sum of the reciprocal primes grow? If you summed all the integers up to x, 1 over n, that grows like log x. So the sum of the reciprocal primes will be slower, smaller than that. In fact, it's a double logarithm of growth. So the sum of 1 over the reciprocal primes over the p's up to x grows like log x. This is extremely slowly growing. This function has never been observed to take large values. I mean, it must, but in practice it doesn't. So I don't think that if you use all the known primes, I don't think this sum of 1 over p up to x has ever been observed to even be 4. Okay? So in any case, the heuristic to address the questions that were asked about this is that the number of Wieferich primes to base a is expected to grow like log x. The number of Wieferich primes up to x is extremely slowly growing. So the examples of base 10, if you look at log 487, that's the second Wieferich prime to base 10, log 47 is 1.8. Oh, that's around 2. Or if you look at the 56 million number, log that is around 2.8. Oh, that's around 3, the third Wieferich prime. We only know 2 Wieferich primes, 1093 and 3511 to base 2, up to like 10 to the 18th. If you look at log 10 to the 18th, that's like around 3.7. Okay, maybe we're hoping the number is around 2, but this is an asymptotic statement, and these values are so small. And not until like log x was on the order of like hundreds and thousands should we expect that the numeric should be any kind of real evidence of what's going on, which is why Nick Katz made this comment here in a paper he wrote where he said that, you know, this heuristic model suggests there should be infinitely many Wieferich primes to each base, but a computer will never convince us of that, right? Because the number of examples is always so small. The model explains why there seem to be so few examples. They're so thinly distributed. So it's not known for any base, whether specific base or pure existence theorem, whether there are infinitely many Wieferich primes. It's not even known if there are infinitely many non-Wieferich primes, unconditionally. Okay, so we expect both of these sets should be infinite. The first set should be almost all primes, but neither has been proved to be infinite unconditionally. Maybe you assume some other conjectures, you can say something, but the infinitude of these sets has never been established. No, not the Riemann hypothesis. The ABC conjecture has some implications in that direction. So let's address the question that was asked. What happens if I increase the modulus up to p cubed? For example, if a is an odd number, if you take p equal to 2, every odd number squares to 1 mod 8. This is a very useful fact to remember. I mean, if you do number theory, it's a useful fact. It's not like, you know. But, and if you want to see another example, like 68 to the, take p equal 5, 68 to the 4 is 1 mod 5 cubed. So aside from the case when p is 2, it's not so easy to find examples of this phenomenon that a to the p minus 1 could be 1 mod p to the third. But if you want to develop a heuristic, how many such things, such primes should you expect to find? Well, now you should think about a to the p minus 1 over p being 0 mod p squared instead of 0 mod p. And if we think about it as a random number, mod p squared, the chance that it would be 0 would be 1 over p squared. So the expected number of such primes p up to x would be like summing 1 over p squared, the probabilities, up to x. And that sum converges, right? Even the sum of 1 over n squared over the all positive integers converges. So this converges. And so the expectation is that there should only be a finite number of these primes. Infinitely many Wieferich primes with the modulus is p squared. But if you fix the a and ask for p's that make the congruence work for p cubed, let alone p to the fourth and so forth, we think there should only be finitely many. Again, a computer is very unlikely to convince us. If you fix a and look for the p's, it's going to be pretty hard. It's already hard to find Wieferich primes. Try to 1093 and 3511 do not fit this congruence for a equal to 2. Okay, so this has never been observed to happen when a, not p equals 2, a. You don't want to confuse your p's and your a's, right? So yeah, when a is 2, we don't know any examples of this. So if you take this idea of, if you have some quantity in modular arithmetic and you don't understand how it behaves, you suppose maybe it's random, you get a probability, you can add up the probabilities. If it converges, you expect finitely many examples. If it diverges, then you expect infinitely many examples. It's kind of a key probabilistic heuristic in number theory to tell us how things might look. So the last connection that I want to make is to Fibonacci numbers, which is not normally something that you see in the context of number theory, but it turned out that if case 1 of Fermat's last theorem failed for exponent p, then you get a certain Fibonacci number is 0 mod p squared. The p minus Legendre symbol 5 on p Fibonacci number is 0 mod p squared. So p is 1 or 4 mod 5, a certain fp minus 1 is 0 mod p squared, if 2 or 3 mod 5, fp plus 1 is 0 mod p squared. So this funny Fibonacci number is always divisible by p, but to make it divisible by p squared, this is hard. And in fact, you can describe this phenomenon of the 0 mod p squared for the Fibonacci number in terms of, if you go to z bracket 1 plus root 5 over 2, the ring of integers of q adjoin root 5, and take the golden ratio phi, then the phi is a unit. And if you look at minus phi squared and look at it in the ring z bracket 1 plus root 5 over 2, you look at it mod p or mod p squared, the unit should be equal. That's equivalent to this Fibonacci condition. It's not obvious, but I'm saying this theorem here relating Fermat's last theorem to Fibonacci numbers can be described in a similar way to what I said before about orders in modular arithmetic, mod p and p squared being equal, but now you have to work in a bigger ring, not in the integers, but in the, doesn't have a name, the golden ratio integers. I don't, it doesn't have to have a name. Call it Bob. I don't know. All right. Anyway, and again, the probabilistic heuristic suggests that these things should occur infinitely often, but extremely rarely. In fact, no example is known where fp minus 5 on p is 0 mod p squared. No example has ever been found. But we think there should be infinitely many examples. Last thing I want to mention is Wilson primes. Just because we're talking about congruences mod p, whether they could work mod p squared. So take Wilson's theorem. If p is a prime, p minus 1 factorial is minus 1 mod p. That's Wilson's theorem. And so a prime will be called a Wilson prime if it happens to also be true mod p squared. And there are only, so for example, p equals 5 is an example. 24 is minus 1 mod 5 squared. So we only know 3 examples. They're up there on the slide. But if you go through the same probabilistic heuristics, we expect infinitely many examples, but no more have ever been found. And so Vandiver had the following amusing comment in the 50s that if he ever came back to life after dying and somebody told him that we had determined if there are infinitely many or not, drop dead again. So that's where I'll stop. Thanks.